Yeah, since we have a small crowd today, only 2 people, so let's make it interactive. Yeah. So Siddhant is joining. So I'm going to share my screen. Yes, let me start. Yeah, last time we gave, we saw an introduction. Yeah, so I did a recap on predicate logic, defined its syntax and semantics. And as illustration, we looked at some examples. So I had given as a class exercise this set of examples. So let me take that. So specifically, I wanted you to, uh, you know, yeah, that's number 6. Okay. So I've already given you the answer. So let me, who wants to give an explanation? I want to, if you figured it out and, got an explanation for why that should be true, I want to hear from you. Okay. So let's see, Anli, were you able to figure out why that had to be true? Can you give why that has to be true? True in the sense that is valid, for all models. Were you able?
So I actually got confused back at point 4, which
Okay, so let's look at it. So point 4. So if you want, we can, because it's kind of important. Although, yeah, I mean, quantification may not figure in all of it, but I think it's important that you understand, since we are going through the semantics. Let's take it. So what is it that you did not? I mean, so let me. Yeah, can you? What is it that you did?
Here it means that for every x there exists some x for which every y has the property of qxy.
That's right. So what does the
But that doesn't imply that every y will always have, for all y there will always have some x.
Correct. So what the precondition formula behind the turnstile says is there exists. Yeah, it is true for those models in which Q is such that there exists a one x, okay, in the range of Q, which is related to every element in the domain. Okay. Yeah. Therefore, here you're saying, the right side is asking if for every y, if I can find an x, for every y in the range of the relation Q, there is a second argument, if I can find an x. Okay. Of course, you can find an x because there is that one particular x. The assumption guarantees that there is that particular x, which maps to every element in the range, okay, for every y. No, you can always pick that. For each y, you can always pick that one element, okay, that is guaranteed to exist by the precondition. Do you understand that? So it's asking for every element y, which appears as the second argument, if I can find an x such that x relates to y for Q. But the assumption already guarantees you that there is at least one x which relates to everything. So I can always pick that x. Yeah.
So, but there can be some y for which that are not related to X by the assumption?
No. That are related to that. There can be some Y that are not related to
X.
no, but because what does this say? It says there exists an X such that for every Y, X relates to Y. Okay. Yeah, there can be some, no, X is related to every Y in the domain. That's what the assumption guarantees. Okay.
But there exists only some X, not every X.
Not every X. That is okay. Okay. But what is this? That's yeah. So I can always pick that X to see this Y here that appears. It is deliberately confusing. See, it's for every Y. Y here appears as a Y appears as the second argument. So what the yes. So there exists an X, right? You're right that there can be Y's. The second argument, which may be there might be some X's which may not be related to Y, but there is one X which maps to every every Y in the range. Now, what the right side is requiring is, for every Y, can I find some X? Okay. For each of those, if there exists, for every Y, which appears as a second argument here, okay. So if I can find some X some X which Q maps such that Q maps X to Y. Because so I can pick that X. No? So this is not requiring, you see, the quantification is reversed here. Okay. What this is asking is for every Y, if there exists an X that maps to Y. Okay. So the right side can, in the right side to satisfy, you can pick different X's. But even if there are some X's which may not map to some Y, it doesn't matter. But there is one X. It's almost like this thing. Okay. So if I can take, so what the right side is guaranteeing is X. Okay. Suppose there are 3 elements in the domain. Okay. 1, 2, 3. So one, what the right side guarantees is one is mapped to Q of 1, 1 is true. 1 maps to everything. Okay, let's suppose my domain. Okay, only has 3 elements, say. Okay, so what the right hand side says is there exists one element, exists an X, such that that maps to everything. Let's suppose that element is 1. Okay, so 1 and 1 is related, 1 and 2 is related, and 1 and 3 is related. These are all true. Okay, agree?
Yes, sir.
Okay.
Mm-hmm.
What does the right side requires? So the right hand side says for every Y in the domain, there must be an X such that QXY is true. That's actually true because that element 1 itself serves as that, isn't it? So here I'm looking at 4. So it is saying for every Y, that is for every Y in the domain, which is 1, 2, 3, it's asking if there is an X such that QXY is true. That is true. Why? Because for 3, I can choose 1. For 2, I can choose the same one. And 3, I can choose the same one. Okay. For 1, I can choose the same thing. So you see, there might be some X's which are not mapped to anything, in this case 2 and 3, but still the right-hand side of 4 is true.
Yes, I got it.
Yeah.
Mhm.
Yeah. What you should do is you should put, yeah, it helps maybe for you to put parentheses after every quantifier and then see that. Okay. So if I put parentheses around the existence quantification, what you have to do is for every I, if there is an X, such that X relates to Y. Okay. But the left hand, the assumption really guarantees even stronger. There's actually one, one unique X, okay, which maps to every element. Okay, and there can be more of those or only one of them. It doesn't matter. Okay, but I can always pick that. Yeah, because the right side is true even when that X is different. It could be different for different Y's. Okay, but the left-hand side guarantees that the same X can be chosen to relate to every. Okay, so that's what it's doing. Okay, so so let's try. So try somebody else. Okay, Chandradeep, did you get a chance to do six?
6. One moment. One moment. Can I share screen?
Can you explain? You want to share or it'll be?
Okay. So for 6, the negation is not of for all x, p of x,
Maybe,
and
yeah, if it helps you, let me see who all are there. Okay. See, okay. Let me, you seem to have got. So last time, someone claimed that this is not true. Was it Dhruv?
Yeah, it was me.
Okay. Are you now convinced?
No.
You're still not convinced. Okay, then I'll give Chandradeep a chance. So if
Yeah.
it helps you, Chandradeep, I will stop sharing and make you host.
So, by the way, saying that a formula is true means it's valid. That's what we are claiming, right? In this case.
In this case, that being true means that has to be valid. Yes.
Yeah.
is this visible?
Yes.
So this is the negation of that statement. So this is for all x, p of x, and there exists y such that not p of y. But this cannot be true, right? If for all x, p of x is true, then it cannot be the case that there exists and y such that not p of y. So this entire thing is false. So the whole thing must be true.
Why? Why?
What is going on? Wait a second. How is this the negation of?
No. See, he's taking, okay, this is one way to argue it, okay? What we are asking is that I think you should show the original formula too, since you are sharing. So okay, so you're taking this. So let me go back to the thing, okay? So so you can make the argument. This is all you have in your screen. Then I don't think so you can describe. So let me. Can you relinquish being a co-host? Yeah, I'll share. Okay, because it's always would be useful to see the original formula. So what he's taking is he's taking this to prove this is valid. Okay, you have to prove that the negation of that is not valid. Okay. Now, a negation of an existential quantification.
No, not valid. You want to say it's not satisfactory.
I'm sorry, it's unset. It's unset. Okay, everyone agree with that? Okay. So negation of for all x is, so there is this thing that holds good. Okay. Negation, I didn't explicitly say, so it's good that we have, of for all x, x. See, as per the semantics, since this requires that for every x, px has to be true. That's when for all x is true. Because the negation by the semantics of this is equivalent to, or let me take the other one. Sorry, there exists an x such that p of x is true. We're taking the negation. Don't confuse with that p that I have there. So I'll use some of the q. We can have it can be any formula. So the negation of this thing is okay. See, there exists an x of q of x. If it is, that's what this thing is asking. If that has to be valid. The negation of that is that for every x, it should not be the case that q of x is true. So this is equal to negation of this one. Correct? Because this thing is implied by the semantics, the way that we have defined the semantics of existential. So if you want there not to be any element x, okay, for which qx is true, then for every x, not of q, I'm sorry, okay, has to be true.
No, so there should not be a negation outside
there
there,
should
right?
not be a negation outside. Sorry. So that's what. So for every x, not of q is true, then there's no way that you can have an x for which q of x for every element in the domain, if not of q of x is true. And that's what he's taking, I presume. Correct, Chandradeep?
Yes.
Okay, now
He had a negation outside that for all.
yeah, but that is, yeah, you had a negation. That's what was probably confusing.
Yes, I did not have the negation at before the exists. So there was a negation before the for all.
Yeah, but you should be showing that this thing is unset. Huh?
So may I have an attempt at my explanation as to why I feel it's not true?
No. Then we'll be spending too much time. Okay.
Okay.
So what is your argument, Chandradeep? Yeah. So you started with this. So were you arguing that this second one is unset? So here, so you were taking exists. Okay. So fine. So he was taking exists. This one. Okay. So this one is the same as negation of see, but what you're saying, what you had something like this, correct?
Yes, and it came out to be true.
Yeah, so this is also okay. So for all x, yeah, so that is also, that's fine, okay? So for all x not of qx, that's the negation of exists, as we have seen here, okay? So he's taking double negation, okay? This thing is negation of exists, so he's taking another negation, so this is fine, okay? So if we plug into q, okay, into q, what are you plugging in? So in place of q, you have,
it will be px and there exists y, not p of
yeah.
x.
So for people, okay. P of X implies for all Y, P of Y, okay? So implication means this is not of P of X or P of Y, correct? So you have to take the negation of that, okay? So if you take the negation of this is what Q is in our case, yeah?
Yeah.
For people to follow. So not of Q of X is P of X. And you have and not of this, okay?
There exists not of Py.
Yeah, which is what you had, correct?
Yep. No, it should be there exists Y such that not of Py.
Yeah, you take the negation of that, okay? So which will be exists Y such that P of Y.
Not of Py.
Not of, okay. So this is what he would have in this.
Instead of not of Qx.
Okay.
Yeah.
So why would this always be true?
We have to prove that this is unsat. Or rather, yeah, the not
Yeah,
of this
is false.
valid.
Yeah.
So,
So it cannot be the case that
continue, sorry.
Yeah, Chandra, you continue.
it cannot be the case that for all x, P of x is also true and there exists an Y such that not P of Y is also true.
Yeah, but because by this equivalence, okay, so because you see for all x, P of x, okay, is, yeah, but this negation is,
Can we just state what we are trying to
Yes,
show?
the
We are
negation will
showing-
make it true.
Hold on, Chandradeep.
The
We
for
are
all
trying
part
to
is
show
false,
that
so the negation
everything
will-
inside the larger parenthesis is unsat. That's what we are trying to show, right?
correct, yeah.
Okay. So if we give a satisfying model to everything inside the bigger,
No. For example, so this is, see, whereas this for all is, by the way, is, okay, let's be careful about the parentheses. There is a parenthesis here, correct?
correct.
Yeah. See, that's why I think your argument, see, arguing this thing, it's for all x, it's px and exists y not of py. So, Chandradeep, I think you had mixed, okay? This is just as hard. I don't know why this should be unset, okay? It should be.
Why won't it be?
Yeah, so like in the interest of time, okay, let me give a solution, okay? So, and you can argue. So for example, okay, we are taking only models of X. Okay, you have to write it down, okay? So, so here's my argument. If you want to come up with an argument, you can put it on a paper and then do it. Here's my argument. So, see, so we are assuming that there is at least one element in the model. Our models are not empty. Otherwise, this is vacuously false. Okay. So now, if there is at least one element in the model, now P can be a predicate which is, say, true, which can either be true on every element, that it is true on all elements, or there will be some element, at least one element for which it is not true. Do you all agree?
Yeah.
Any model, either P will be a predicate which is either true on everything, on every element, or there will be one element, one or more element for which it is not true. Let's take the second case, for first case, for example, if it is, okay, the second case, if it is, there is at least one element for which in the model P is not true, then I can take X to be that element for which P is not true, okay? So then what happens? Then what does this logical implication reduce to? Because if the antecedent of logical implication is false, it is
True.
true. Okay, so I can make the existential the quantified formula satisfied by picking that X for which P is false. Okay. Now, let's suppose that P, in the model, P is in those models in which P is true everywhere. Then what do you have here? P of X, then I can choose any X for that matter. Because for any X, P of X is true. This will be true. The antecedent will be true. And what is the consequence? Consequence says for every Y, P of Py is true. That is already true. Why? Because P is, this is the case where the model maps P to a predicate which is true everywhere. So what you have is true implies true. Therefore, it is true. So, see, yeah, so you have to split into two cases. Now, I think Chandradeep, by doing this, you will have to similarly argue. I think you got confused with the nesting of the quantifiers, okay? Because this one has for all X, Px. It is not, so you'll have to rethink that, okay? So your argument as to why this thing is false, I think you can get it, okay? That argument also. It will be somewhat similar to the argument you'll have to use in order to prove that this is unsat. Yeah, or in this case, you're not proving that this is sat. You have to prove that this is always true, or at least this part here is always false, okay? So at least you didn't give a complete argument as to why that should be false, yeah?
Yes, so for the conjunction to be true, P of X must be true for all X, but if P of X is true for all X,
that is where I'm why? No, because this thing is saying for all, okay, so let's see. So for all X, this thing, for every X, Px has to be true, okay? And there exists a Y such that not Py. No. See, but for every X, Px has to be true, and there must exist a Y such that not of Py is true, okay? So I think the same kind of argument you'll have to make, okay? Because suppose P is true, for some P is true, for some P is false, okay? Yeah. So then, it cannot be the case. I think so. Yeah, I agree with you, Chandradeep. So you can say that for this to be true, for every X, the first conjunct has to be true, which means Px has to be true, okay? But the only problem is you cannot just deduce with that thing, because it depends on what the interpretation for that P is. If P is true for some X and for not X, then P of X cannot be true on all X. Okay, so that's the kind of argument that you'll have. Yeah. Okay. So
no, if P of X is not true, then it's already false. Everything gets false.
That's what? No, but suppose P is true for some, P is true, P is false for some.
In that case, the whole for all part is false.
Yeah, that's right.
We have
that can also be, yes, you're right. Okay, so that can be a good argument. Yes, because for it to be true, the first conjunction has to be true everywhere anyway. Okay, and but if it is true everywhere, then the second conjunct cannot be true. Correct? Because that says there exists an Y such that not of Py is true. Yeah. If P of X is true, for the first conjunct to be true, P has to be true everywhere. Okay. But if that is the case, the second conjunct will not be true. Yeah. Because that requires that you must find at least one Y at which P of y has to be false. Okay, and therefore you cannot have it. Yeah. So that's the way that you'll have to make the argument. So in the sense that that part was what was kind of implicit in your argument. Okay. Yeah. Yeah. So see, I want to move on. I mean, if you still have doubt, I urge you to kind of yes, split this thing. Consider the case where P is, the models have to be split such that where P is true everywhere and P is true, not true everywhere, but there are some things which is true. So that's what is the argument that comes here, okay, in Chandradeep's thing as well, okay? Because both these conjuncts cannot be true simultaneously if for all x that conjunct has to be true. Yeah? I think we have spent a lot more time than what I would have cared to, but that's okay. Yeah. If you're still confused, what I want you to do is to think through it, and then we can individually discuss, okay, where you have a disagreement, okay? Yeah, Dhruv, are you convinced now?
Oh, hi, sorry, I was muted. Yeah, I'm convinced now.
Okay, just to finally to recap. Okay, so what do we have? Phi is satisfiable. Okay, these are the things that we went through. Okay, just to recap, in this predicate logic, it is, there is this notion of satisfiability, which means there is an interpretation and evaluation. It's missing here, which satisfies it. A formula phi is said to be satisfied by a model if for all the interpretation that the model gives for the function symbols, etc., that this semantic function should be true for all possible valuations sigma. If it is valid, it should hold for all interpretations for all valuations. And then we also introduced, usually logics have this notion of logical implication, which says given a set of formulas, well-formed formulas in the logic, we say that tau, or gamma, phi, gamma logically implies another formula phi written this way. If for every model and every interpretation that satisfies all the formulas in gamma, okay, for every such model and valuation, phi should be true for that valuation. So we are, so this is a way of saying that if you restrict yourself to models for which every that make every gamma, every formula in gamma to be true, then for that valuation and models, that phi has to be true as well. Okay, that's the semantic notion of logical implication. Okay. Now I'm going to introduce inference rules, proofs, and decision procedures. Just like, so for predicate logic in general, you already seen an inference rule is, or a schema, it's usually has parameters. It specifies when a formula of some form phi can be derived from a set of other formulas. It's usually written this way, that I can derive phi, any formula of the form phi from some other formula. That's what the inference rules says. So a deduction system is a finite set of inference rules for a logic. Okay, so the purpose of a logic is to solve this problem of logical implication. Okay, and these rules are given. You saw the example of the resolution inference rule. So deduction system consists of a finite set of inference rules for logic. Then a proof is a tree where every node in the tree is a formula. It's more like a derivation of a conclusion from a set of assumptions, starting with a set of assumptions. But the way it is done is through application of these inference rules that belong to a deduction system. So a set of inference rules is called a deduction system. So a proof is a tree where every node is a formula in the logic, and every edge is an application of an inference rule in the system. Okay? So let's suppose that gamma be so in such a way that gamma is the leaves of a proof, and phi is the root. Then we say that the proof deduces or derives phi from the assumptions in gamma, and that's usually written by this single turnstile, okay, turnstile implication. So this is a way of kind of automatically deducing through the application of inference rules to prove. It's a proof of showing that phi follows, gamma logically implies phi, or phi is implied by the set of set of assumptions, the conjunction of all assumptions in gamma. Okay, so I mean, deduction system. We're not going to go into the various deduction systems, but predicate logic, like propositional logic, which is part, has different kinds of logicians have come with different kinds of deduction systems. Some of the prominent ones are secant calculus, natural deduction. We already saw the resolution principle or resolution inference rule, which was that single inference rule is a deduction system that can do logical, that can be used to derive proofs of logical implication of one in propositional logic. Similarly, there is an extension of resolution rule called paramodulation, which also is is a deduction system that can be used. So once you have these deduction systems, but like SAT solvers, and there is we already talked about this. Okay, decision procedure for a logic is an automatic method of checking if phi can be derived from a set of assumptions. Okay, so this can be viewed as a way of automating the search of proof within a deduction system. That is one way to view it, or it can be completely a different algorithm. Okay, for example, SAT solvers, although at the core it was using a special kind of resolution, it had lots of heuristics and so on. Usually decision procedures can be viewed as applying some inference rules, but they also use a lot of other tricks. So that's what SAT solvers and SMT solvers actually do for different logical systems. We already saw one for propositional logic, that is SAT solver. A little bit later in the course, we may, I might, if I find the time, discuss a little bit about SMT solver, but I will not do that right now, because the emphasis of the course is to get into see how predicate logic can be used for software verification. Okay, now you've already seen, I don't know, I mean, if you've taken the logic course, you will see. So there are two very important notions of for logic, which are really properties, attributes of a deduction system that one has. So this can be applied to a decision procedure also. So this is, one is soundness and the other is completeness. And I think this is important for you to do. This relates the two notions. Okay, so we talked about proving logical implication using a deduction system, which consists of inference rule. And we also defined it in a semantic way based on if the models, if all possible models in which every formula gamma is satisfied. So this is completeness and soundness relate this semantic notion of logical implication with the deductive notion of logical implication. This is more like a mechanical derivation. Okay, that's what this thing says. So soundness says that if I can derive a formula phi in a logic from a set of assumptions in gamma, we are strictly by applying the inference rules, then it has to be semantically sound, in the sense it has to be, if it can be deduced from tau, then gamma should logically imply phi in the sense of the semantic way that I defined, okay, based on models. Okay, so that's what I mean. It relates this. Okay, so you don't want a proof to prove a formula phi, to deduce a formula phi as a consequence of a set of assumptions, and then had to be false, and that phi to be false on models for which when every formula in gamma is true. That's what it guarantees. So soundness is very important. See, this can be established as long as every inference rule in your deduction system is itself sound. Okay? And we saw that that's how that you normally prove. And we saw that in the case of resolution, okay, that the resolution principle was sound in that it, with respect to the, using a model in a model theoretic way. The completeness goes the other way around, okay? It, says that whenever phi, is logically implied by a set of assumptions, that the double turnstile as per the semantic notion, then I can always produce a proof using the inference rules in the system. That's what completeness says. It's, so soundness is like kind of a correctness, okay, that you don't end up, proofs don't end up deriving false conclusions and sound, whereas completeness is an attribute of a deduction system, that every consequence that follows as a logical, that is logically implied by a set of assumption can be derived, okay? In that sense, when a deduction system is complete for a logic, it means that that it is powerful. The inference rules are sufficient to derive every possible formula that is logically implied by that. Okay? So, and this concept can also be applied to decision procedures. By the way, so I said this logical implication, both validity, satisfiability, and unsatisfiability can always be expressed as logical implication. Okay? So for example, validity means that you should be able to prove phi, okay, using the inference rules with no assumptions, okay? That's how you establish tautologies, okay? Proofs of validity, you should be able to, if a set of, that's how it can be expressed as a proof with logical implication, okay? So starting with no assumptions, if you're able to, prove phi using inference rules, then you're proved phi. Or you should be able to start with phi and then derive true, if true is a constant. Okay? Similarly, unsat can also be expressed as deriving false using your proof. Okay, that's why this logical implication can be used to prove validity as well. So if you can derive false, that means it is unsat. And that's how using deduction system that you do. Now, as I said, the concepts of decision procedure, the concept of soundness and completeness can be applied to decision procedures too. What that means is that so if a decision procedure is said to be sound, so whenever for example, if whenever a SAT solver which says a formula is valid, okay, or is valid, then it indeed has to be semantically equivalent to true. So whenever it says it's unsatisfiable, then it means that it is it has to derive a contradiction. Okay, and that's how it'll be true. And also, if it is complete for propositional logic, if every formula that is valid can be checked by your SAT solver. Okay. Any questions? Okay. Now, so we also introduced this. What do, so this is here, all the proofs and your decision procedure for all models, but whereas what happens in SMT is what differs satisfiability modulo theory from decision procedures for general predicate calculus is that you extend this notion of satisfiability, unsatisfiability, and validity to formulas in which the restrict yourself to a particular domains and interpretation for the functions and predicates. Okay, and usually that particular interpretation that is given by by giving a set of formulas. The presentation, the description of the domains can be described as a set of formulas, because a set of formulas can always, the domains can be assumed to be those models or those models for which every formula in that theory is so the domains include every the domain, and I'm sorry, the model includes every thing for which every formula in that theory is true. So example theories are of these things that we talked about. Okay, and now if you restrict yourself to specific theories and so on, then you can talk about validity and satisfiability relative to those theories which define the specific interpretation. Okay, so like either you have your domain as integer arithmetic, real arithmetic, or bit vectors, or any combinations of these things. Okay, so then it's usually called T valid, T satisfiable, and T unsatisfiable, and you can use this. You can extend this notion. So we say that a formula is T valid if and only if it is for every model, for all models that satisfy the theory T, which means every formula in that, and for all variable assignments, your formula has to be true. Okay. Similarly, it is T satisfiable if there exists some model M of T and a variable assignment such that phi, that formula is true for that model and for that valuation. Now, if it is said to be unsatisfiable if it is for all the models that you care about, okay, which means for all the models for which the particular theory that is of interest to you, for all those, for none of those models that for which the theory that satisfy these formulas in the theory and for any variable assignment, it should be the case that phi should be not satisfiable. Then it is unsatisfiable. Okay. So that's so that's what this validity. That's what validity problem relative to these theories really mean. So I show you an example here, and this is what SMT solvers do, which are the engines behind tools like CBMC and so on, you really do what is done here. Sometimes, although this validity and SMT problem, the way we have presented it is for predicate logic with quantifiers. Usually when you throw in quantifiers, it becomes undecidable. So what SMT solvers do is they restrict the decision problems to the quantifier-free fragment of predicate logic. Okay? So we assume then that there are no quantifiers. Okay? And here are some examples. So for example, so here the first one is propositional logic. Okay. Yes. Okay. So this is pure proposition logic. Okay. And that is, there are no theories. Okay. Where it becomes more interesting is now I've thrown in equality. Okay. So equality, and this is a formula with predicate logic, quantifier-free predicate logic. You see all these formulas do not have any quantifiers, but you can, so then the satisfiability problem and validity problem of these things, okay? For example, y1 is equal to, here the theory is theory of equality, okay? So I have equality, and the domain over which the variables can range can be some arbitrary domain, okay? It does, it can be integers, any domain for that matter. But I'm restricting myself, and the only predicate symbol that I have other than the logical symbols is this equality, okay, which corresponds to the identity operator. And usually, I mean, since that satisfies the axioms of reflexivity, commutativity, and transitivity. For example, is this, and SMT solvers can solve this. Okay, so this formula y1 is equal to y2 that is shown here. If y1 is equal to y2 and y1 is not equal to y3, can y1, well, there's a mistake here. Can so y1 is equal to y2. Is this, so now we can ask the question if this is satisfiable. This is what is called, it is a formula in the theory of equality. Okay, is that satisfiable?
Yeah.
Yeah, suppose I changed y2 equals y3.
Then no.
Yeah, okay. So y1 is equal to y2 and y1 is not equal to y3, then it came out. Because that, why is it not? Because it does, it violates
Transitivity.
the transitivity. See, that's what. So I hope you understand why it is called satisfiability modulo theory, okay? The theory here is giving a specific interpretation to equality, which assumes that the transitivity, commutativity, and associativity laws of equality are satisfied. So, and that's what SMT solvers do. They are able to do this. Now, you can have linear arithmetic where plus and minus are given the standard interpretation, okay? And less than or equal to is the linear inequality, okay? Now, of course, you can have what would be the theory here, okay? So, you cannot, integer arithmetic and real arithmetic, they cannot be, they can be, axiomatized. You can also have theories describing them. Of course, we'll have to have an infinite set of axioms, but they can be expressed as finite schemas. Yes, a set of finite schemas. But nonetheless, so you could assume that if given specific interpretation, then how can you solve this? Okay, these things. Now, can linear, see, you already know linear programming is a decision procedure can be used as a decision procedure for a set of a conjunction of linear inequalities. Okay, but what SMT solvers do is it extends that to arbitrary propositional combinations. You see here, this particular formula, okay, it cannot be solved by an LP solver. Okay, you guys, I'm assuming you're familiar with LP solver. Why? Because it has a disjunction. Okay, LP solvers can only do only conjunction. So whereas SMT solver can use such decision procedures for specific theories or combinations of specific theories and solve arbitrary propositional combinations of those atomic formulas. Similarly, you can have bit vector operations which have whose meaning can be given by a set of axioms, okay? Or you can have standard, some standard interpretations with domains and so on, or arrays. So specifically what SMT solvers do is they support not only these infinite precision arithmetic theories, but they also support those kinds of domains and models that capture the semantics of data types that are used in typical programming languages. For example, for C verification, you of course need bit vectors, arrays over discrete indices, the pointer logic, and combinations of these things. Okay, so that's what SMT solver does. Okay, so so these kinds of things you can actually type in this to Z3. Okay, and the interesting thing is you can combine all these things in whatever way you want. Okay, for example, here, look at this example, the third bullet. Okay, it combines arrays, okay, with index and select and update operations, and arithmetic operations, assuming if the elements are over real, or arrays, the elements of arrays are reals, then you can have formulas of this kind that combine, where the atomic formulas are from different theories. Okay, so here this is an example which combines linear arithmetic and arrays. Okay, similarly, you can have function symbols which are uninterpreted. In this sense, they can be anything, and you can have equalities and arrays and so on. So that is the power of these things. So I was so this is all mostly SMT solvers do it for quantifier free. By quantifier free, what I mean is when SMT solvers decides the satisfiability of that a formula is satisfiable, implicitly it means that it is deciding see, when a particular formula is satisfiable, what does it mean? Because after all, this satisfiability it is doing only for specific models, okay, that give specific meaning. So when you say it is satisfiable, it means there exists a value assignment for the variables in the formula for which that can make this formula to be true. So that is the same as saying there exists, in this case, y1, y2, y3, such that this formula is satisfied. So the satisfiability, so in that sense, when it says something is unsatisfiable, it really means that the negation of that formula is valid. Okay, so which means that the negation, or the negation of it is true for all. So implicitly, when I say SMT solvers decide the quantifier-free predicate logic for specific combination of theories, what I mean is that it kind of allows quantifier only at the universal and existential quantifier at the outermost thing. That's what it means. What it cannot do is solve things like for all x does there exist x. Okay, the kind of examples that we saw earlier in the predicate logic example that I gave you, those kinds of nested quantifiers, typically SMT solvers that are able to solve quantifier-free. So when I say quantifier-free predicate logic, it means that you can't have alternating quantifiers. Okay, is that clear? Yeah. Any questions?
So it's possible to have nested quantifiers of the same type.
No. Okay. What I'm saying is typically when I say, there are SMT solvers that can, so like I said here, SAT modulo SMT solvers, they combine SAT solver and decision procedures for the conjunctive quantifier-free fragment of specific theories like linear arithmetic, real arithmetic, linear integer arithmetic, arrays, pointers, etc. Okay, and usually they only solve quantifier-free. Okay, what that means is that because they also do validity and satisfiability, what it means is that it means that either you can interpret it as no quantifiers or just one quantifier at the outermost level. It usually does not allow alternating quantifiers. Okay, but some SMT solvers that I think have I made that clear? Okay.
So you're saying it's possible to have there exists x, but not there exists for all y.
Something like that. Because there exists an x with only one quantifier is the same as the satisfiability problem.
But it's also not possible to have there exists x, there exists y, is it?
No. But that, see, if you only have existential quantification, that you can reduce them to one single quantification. Okay. So nesting of the same kind of quantification doesn't add any more expressive part.
Yeah, that's what I was asking. Actually.
Yeah. Oh, that's what you're asking. So that's a trivial thing. What I meant was things like where you can alternate existential and for all quantifiers. Okay. Now you can extend them to those things, and we will look at that. Okay. Some of our synthesis problems, when we later in the course look at synthesis problems, end up solving those things, end up having to solve a certain level of alternation of quantifiers. Okay, there some SMT solvers do support, some, if you in some limited circumstances, some alternation of existential and for all quantifiers, but not all of them. Okay, so that's what I wanted to say. So. So this is kind of the architecture. Okay, so SMT solvers have a core. What they have is what are called decision procedures for individual theories. Okay, for arithmetic it can be using LP solvers or simplex things. For arrays they can be special purpose decision procedures that solve the decision problem of the quantifier-free fragment of a conjunction of formulas. Similarly, for bit vectors, what SMT solvers add in this core is like an extension of a DPLL SAT solver that interacts or that interfaces with these decision procedures to solve the satisfiability problem of arbitrary propositional combination of atomic conjunction of atomic formulas drawn from these theories. That's why it means that this SMT solvers with the special purpose DPLL at its core, it can solve the quantifier free fragment of predicate logic. Okay. I've already shown you some examples of the kind of things that it can solve. Okay, you can actually go to Z3, type in these formulas, and check. Okay, and make sure that it works. Both satisfiability and unsatisfiability. So do a SAT and unsat check. Now Z3 can also do some quantifiers. Okay, so you can throw in some quantifiers to see if it works. Okay, even alternating quantifiers, see if it works. Okay. By the way, Boolean you can add quantifier by adding quantifiers to proposition logic. That logic is called quantified Boolean logic. Okay, does that add any more expressive power than propositional logic? Can anyone answer? Suppose I add quantifiers where the variables are just ranging over only Boolean values, 1 and 0. So that kind of a logic is quantified Boolean logic. Okay. See, if it's only ranging over Booleans, you can always eliminate, right? For example,
basically enlist all possibilities, right?
That is right. Okay, so that's fine. So for example, what does for all x or y mean? Okay, if x is only Boolean, this is equivalent to 0 plus y and 1 plus 1. Okay, so you can enumerate all the values, and that's why adding quantifiers really doesn't it doesn't add any expressive power, but still quantified Boolean formulas are useful because you can express doing this way of if you can solve the quantifiers without actually doing this expansion, which will have an exponential blow up, there are decision procedures that can solve quantified Boolean formulas without doing this expansion. Okay? And so that logic is decidable. Okay? And so is, for example, you must have heard of a Pressburger arithmetic. Okay, Pressburger arithmetic has plus minus. It has successor 0, but it has you can do induction principle. Okay, and the logic allows for universal quantification. Okay, as long as you can derive from induction principles or things like that, and negation of those things and so on. So, but if you restrict yourself to only to plus and minus, successor and 0, that thing is decidable. Okay, so there are logics of that kind which are decidable. So it's 6:15 already, so I'm taking a lot more time than I'm going to stop here. So I thought I'd be able to get to introducing Hoare logic, but I will stop here and take. There are some complexity things, even for the quantifier free conjunctive formula. The decision problem for these theories are pretty hard. Okay, and then what SMT solvers do is add a layer of DPLL on top of that. Okay, so I'll stop here and take any questions you might have. Okay, so we're meeting tomorrow. So starting tomorrow, probably it'll be we're looking at real software and logic for software and so on. Yeah. Okay.
Thank you.
Thank you.